Okay, so in lesson 8, we're going to look at the equations of planes now. So we've talked about certain planes. We talked about the xy plane, the xz plane, and so on and so forth. So just to make sure we're all on the same page, a plane is a two-dimensional flat surface that sort of lives in 3D. So a flat surface that lives in 3D. So the xy plane is a plane. So sort of this area that extends forever and ever and ever, that sort of floor that extends forever and ever and ever in all directions, is one particular plane. But planes don't, so those planes are all sort of vertical or horizontal. Planes can kind of be at any weird angle cutting through space. So one way to kind of visualize a plane might be to take 3 points, so say your intercepts of this plane, and sort of picture that that Dorito chip kind of floating in space, connecting those 3 points sort of on a weird angle, and then take that idea and sort of stretch it forever and ever and ever in all directions, up and down, so a flat surface. So that's one way to visualize a plane. Or if, just take any sheet of paper and hold it at a weird angle, and then imagine it's the edges of that paper just sort of extending forever and ever and ever, cutting through everything in its wake, leaving an awful path of destruction. That's sort of what a plane would be there. So what we're going to do is we're going to work first with the vector equation of a plane. So we're going to consider same kind of idea as our vector equation of a line. We're going to have a starting point. So it's kind of weird to think about it on this angle. So what I'm going to do is I'm going to redraw the plane as if we're floating right above it, looking straight down on it. So it's just sort of this rectangular flat surface. And we've got a starting point. And when we had a line, we needed one direction vector. And with one direction vector, you could go anywhere along that flat line. In order to get to other points on this plane, say a point up here though, one direction's not going to do it. Sorry, Harry Styles. Is that guy on one direction? I feel like I nailed it. You need a second direction vector. So we're going to have a starting point, and we're going to have any two vectors that point, I drew those at 90. They don't have to necessarily be at 90. Any two vectors that point in different directions along that plane. So they can't be pointing along the same line, because you got to be able to kind of turn and make the corner. With those two things, we can kind of stretch and get to other points on the plane. So the vector equation of a plane is going to look like this. We're going to have a starting point, so any point on the plane, and we're going to have two direction vectors. So maybe I'll use lowercase d's for the first one and uppercase d's for the second one. And now we need kind of two parameters, a t and a k, because we're going to get to any point on the plane, we're going to have to stretch those to get from your starting point to any other point on the plane. We're going to have to stretch those vectors different amounts, so they can't have the same letter on them. One's got to be t, one's got to be k, or whatever letters you want to use. And so kind of the idea is you start here, and if you wanted to get to that other dot, you might have to stretch, let's say, that vector that amount, and then the other vector that amount to get from there to there. So you're doing sort of stretching the vectors different amounts. And like you've kind of always done something like this, right? Whenever we worked in 2 dimensions, like we called this the point 4, 3, really what you're doing is you're going stretching this vector, like the vector that's 1 along the x-axis, you're stretching it 4, and then stretching the vector 1 along the y-axis, a value of 3. So the point 4, 3 looks like our starting point is the origin always. And I'm doing like a 2D representation because that's just the xy plane, but the idea is the same. You take 4 plus that plus 3 times that. It's that same kind of idea, but now our vectors aren't going to be these simple 1 up and 1 over vectors. They can kind of be on any sort of angle. But you got kind of the same idea. You're kind of defining a grid on this plane, just that grid is now sort of a parallelogram grid instead. So we've got something like that, and something like that to get to different coordinates on this plane. So it's the same kind of idea as you've always labeled points. It's just the vectors that we're using to get there aren't straight up and straight over anymore. But we can still kind of think of it as, if it's helpful, you can kind of think of it as grid points on that plane. Just your grid points are now little on diagonals and whatnot instead of straight up and down. That's the same kind of idea. So that's our vector equation of a plane. And then same sort of idea, we'll be able to stretch that. Break that into the parametric equations. So there's our, these will be 2's now. I'm struggling with my lower cases and capitals. And 3's. So we've got our vector equation. We've got our parametric equations. And then we're not going to be able to do a symmetric equation of a plane because there's 2 letters. So I could rearrange and solve for t, and solve them all for t and set them equal to each other, but there'd still be this k hanging around. Or I could solve for k, but there'd still be a t hanging around. So since there's 2 parameters here, we are not going to be able to make symmetric equations. So we just have vector, parametric, and we will see scalar in a little bit. So we need to find the vector, parametric, and parametric equations of a plane with those 3 points. So see if you can take that intro that I've given, see if you can make the vector a vector equation. There's going to be lots of options for that plane. And then unpause the video and see where I'm at. So my vector equation is going to look something like that. The first bracket is going to be a starting point, so you have 3 choices. You could use A, B, or C for that. Does not matter. And the other 2 have to be direction vectors on the plane. So we've got some plane, we've got an A, a B, and a C. So a good direction vector, we can't use the individual points. They're not vectors, they're just points. But I could use the vector that points from A to C as one. And as long as I don't do CA as my other one, you got to involve B somehow to make sure they're not parallel vectors. So I could do, say, AB and AC as my 2 direction vectors. So A to B would be B minus A. So 3, 7, 9, subtract 2, 4, minus 2, something like that. 1, 3, 11, I think. That can be my first direction vector. And then I can do, say, A to C as my second direction vector. And again, you have choices here. So you could do BC as one of the vectors and CA as one of the vectors. It doesn't really matter. You don't always have to use A, like I did A to C and A to B. They don't even have to start in the same place. I could have done AC and CB. It doesn't matter. As long as they're pointing in different directions and they are on that plane, you're good to go. So AC is going to be C, take away A. Negative 4, 4, and oh, that's a 4, not a 9. Can't read my own writing. So negative 4, 4, and 6. So that will work for that. T and K are real numbers. Don't want to lose my communication marks there. And I gotta fit in my parametric equations somewhere, so I'll just write them over here. So the x components are 2 plus 1t minus 4k. The y's are 4 plus 3t plus 4k. And the z's are negative 2 plus 11t plus 6k. So there's my parametric equations. There's my vector equation. And again, it can look very different You could have chosen any of the points for the first thing, and you could have made vectors in different orders or using different combos. But that's one way to write the equations of that plane, but there's infinite ways to write it. All right, so find the vector and parametric equations of the plane that is perpendicular to this plane and contains the line law. So I'm going to try and draw this as best I can. So we have two planes involved, the one that we're trying to find and the one that they gave us. So I'm going to call this one that I've drawn in red. This is the one we're trying to find. And this one in black is this plane here that they gave us the equation for. So what we need to do is on our plane, we need to first find a starting point. So a point that we know for sure is on our plane. So what we know about our plane is it contains this line, which means that point minus 3, 4, 6 is definitely on our plane because that whole line's on our plane. It also means that that direction vector, 1, 0, 2, is for sure on our plane as well because that whole line's on our plane. So that direction vector definitely points in some direction of our plane. So with just that information, we can fill in most of the equations. So we have a point that we know. We have a vector we know is on the plane we're trying to find. Now, what we know about the other plane is we know some random point on it, 1, 2, 3. Might be one of the points on the line on our plane, might not be, doesn't really know. We know two direction vectors, that minus 2, 4, 6 is on that plane, and 1, 3, minus 4 is on that plane. And again, I'm not trying to draw this in any sort of way that makes sense. I'm not paying attention to the numbers. I just know that I've got vectors on that plane. And I know that that plane is perpendicular to our plane. And so the idea is we've got to find another vector that is definitely lying along our plane. And we know if I could find a vector that's, say, sticking straight out of that plane at 90 degrees, it would be a parallel vector to our plane because our plane's perpendicular to that. So anything sticking straight out of that plane would be parallel to our plane, which means that it would lie on our plane, and that could potentially be our second direction vector. And so to get our second direction vector, we're going to find something perpendicular to the plane that we're given. We're going to try and find a normal vector to the plane that we were given. And we've got two direction vectors. We want something that's going to be perpendicular to both. Oh, that's going to be a cross product thing. So that's going to be our second direction vector, is going to be the cross product of those two things. So I'm going to write out minus 2, 4, 6 twice. I'll write out 1, 3, minus 4 twice. Cross out the first, cross out the last. I'm going to get negative 16, subtract 18, and that is going to be negative 34. I'm going to get 6, subtract positive 8, and that's going to be negative 2. And I'm going to get negative 6, subtract 4, and that's going to be negative 10. Okay, so that potentially can work. So I'm going to now make sure that I've got all those negatives right. I'm going to dot it with one of my starting vectors, so it looks like the second one's got easier numbers, so negative 34. So that normal vector dotted with 1, 3, minus 4, just as a check. And you can just check this on your calculator too. You don't have to write it out, but I'll write it out because I don't have a calculator with me. So we get negative 34 from that, we get negative 6 from that, and we get positive 40 from that. And that looks like negative 40 plus 40, that looks like 0. So it looks like we haven't messed up our minus signs there. So I can use that vector now as my second direction vector for that plane. And there we have it. T and K are real numbers. The question did ask for vector and parametric equations, so we should take a moment and write out our parametric equations as well. So x equals -3 plus t minus 34k, y equals 4. No t's there because it's t times 0, so we're just going to have the k term. So minus 2k, and z equals 6 plus 2t minus 10k. So there's my parametric equations, something like that. All right, so that covers the first two equations of a plane, and the third one is the scalar equation of a plane. And so the scalar equation is going to look like ax plus by plus cz plus d equals 0. And if you remember the scalar equation of a line, the AB vector in the equation of a line was perpendicular to that 2D line. How that sort of extends in 3D is we have the plane, we're going to find what's called the normal vector for that plane. We're going to find a vector perpendicular to that plane, and that can be used as ABC. So ABC must be normal to the plane. So that's how a scalar equation of a plane is going to work, and we'll see that in action right away. So I'm going to go with this example. We're going to have, was I smart and made it the plane that I gave you before? Yes, I was smart. Okay. -2, 4, 6, 1, 3, minus 4. Yes. So we've already done the cross product. That's wonderful. So we're going to take that plane that was the equation in the other question, and we're going to turn it into a scalar equation. So we have a plane, we have the point 1, 2, 3, and we have the two direction vectors. So that's what we're starting with. And we're going to first find the normal vector to that plane. And the normal vector to that plane, how you get a normal vector if you have your two direction vectors, is you do the cross product. That's what cross product does. So cross 1, 3, minus 4. And I already did that and got minus 34, minus 2, and minus 10 the way I did it. And so that vector could work. So I could start my equation with minus 34x minus 2y minus 10z plus d equals 0 and solve. But I'm not going to do that because that looks like a gross vector. And it doesn't matter the magnitude or the direction as long as you're perpendicular. So any scalar multiple of that vector would work. So I will use, instead of that, oh, I didn't do my self-screening this morning. Look at that. I'll do that in a minute, I guess. I'm going to use, instead of that, I'm going to kind of reduce that vector because I can multiply it by any scalar multiple. So I see that they're all negative, so I'm going to reduce it by, and they're all even. I'm going to divide everything by -2. That's going to keep the direction. It's going to give me nicer numbers to work with. So I'm going to use that for my ABC. So 17x plus y plus 5z plus d equals 0. There we go. And now, echoes of grade 9 math, we've got everything but one mass component to find. We've got an x, y, z in our equation. So if we knew a point on this plane, we'd be good to go. We'd be able to solve for d. And guess what? We have a starting point on that plane. Plus 2 plus 5 times 3 plus d equals 0. So 17 plus 2 plus 15 plus d equals 0. So that looks like d is going to be -34 when I swing everything over to the other side. And we can write our final equation. -34 equals 0. And if I didn't if I didn't divide that vector, if I didn't reduce that vector to start out, it might look something. So, and then that would have ended up being positive 72. Absolutely all four parts would be multiplied by -2. So scalar equations can look a bit different, but if they are the same plane, they will be fully scalar multiples of each other. All four numbers will be multiplied by the same amount to get to the other one. So that's what that might look like. And then I didn't give you a lot of justification for this actually being the equation of a plane, so I just want to prove that points on, or at least one random point on the first equation also works for the equation that we found. So we're going to find the point with t being 4 and k being -3. Z equals 1, 2, 3 plus 4 times that vector -3 times this vector. And so what that's going to look like is, if I'm looking at just the x's, 1 minus 8 minus 3 more, so that's -7 minus 10, I believe. We'll see if I get it right or wrong when we try it. 2 plus 16 minus 9, so it's 18 minus 9, I believe. I got 9 there. 3 plus 24 is going to be 27, plus another 12 is going to be 39. So that's a random point on the plane, and I'll just show that that point does in fact work on the equation that we found. So the equation we found, the left side of it would then be 17 times -10 plus 9 plus 5 times 39 and then -34. This will be interesting. See if this actually works or if I screwed up that point. That's -170 plus 9. 5 times 40 is 200, so 5 times 39 would be 195. And then -34. Let's see. Sorry, we're checking to see if this is 0, so I shouldn't put the equals 0 there. So we get the negatives are -204, and the positives are +204. So yeah, that does in fact come out to 0, so that works. So therefore that point is on the equation that we found. So that equation at least works for that random point. It definitely works for the point 1, 2, 3. If you try any point, it will in fact work. That is the same equation as the vector equation. All right. So find the scalar equation of the plane that contains the points blah. I guess I should just summarize what we did. So to turn a vector equation into a scalar equation, we do the cross product of the two direction vectors. We do the cross product of the two direction vectors. I'm looking at the wrong part. To get a normal vector, that normal vector becomes the ABC in the equation. Then you plug in the point and solve for D, and that's how you turn it from vector equation to scalar equation. Just something that we're going to do quite often, so I want to make sure that you have it. So we've got a plane. We've got two random points on that plane. We've got a second plane that is perpendicular to our plane. And that second plane is given to us as a scalar equation. So we know that its normal vector would be the vector 2, -1, 1. That would be a vector sticking straight out of that plane. 2, -1, 1, so that's the ABC from that equation. So that's a vector. So if we're thinking about direction vectors, that would be a direction vector for our plane. It wouldn't be perpendicular to our plane because it's perpendicular to the perpendicular thing. So it would be lying on our plane. It wouldn't be sticking straight out. We have a second direction vector we can get by connecting those points as a vector. So we've got the 3, 2, 1, and 1, 4, 5. We can call that point A, that point B, and do a vector AB is b minus a, 2, -2, -4. We can use that as our second direction vector for the plane. And once you have two direction vectors, you can get your normal vector by doing the cross product. And that will be the ABC, easy as 1, 2, 3 in our equation. So write out the first one twice, write out the second one twice. We get +4, take away -2, so we get 4 plus 2. We get 2, take away -8, so that's writing the answer there. 2 plus 8 is 10. And we get -2, take away -2, so that's -2 plus 2, which is 0. Okay, let's just double check that that's at least perpendicular to one of our vectors, and it's not. What did I do wrong? Because that's 12, and that's -10, so that doesn't make 0. So what did I screw up? Got the negatives in the right spot. -4, +4, minus -2 is 6. No, I did this one. 2, 8, that seems fine. -4, duh. +2, sorry about that. -2, that looks better. Because now that's 12, that's -10, that's -2, so that's going to make 0, so that's going to work. There's our normal vector. That looks better. So, wow, I did not give you any space to write this out, but that's going to be your ABC. So you're going to get 6x plus 10y minus 2z plus d equals 0. And you can plug in either of the starting points. So that would be the point A or point B in my picture. So I'll use A, 6 times 1 plus 10 times 4 minus 2 times 5 plus d equals 0. Starting to write the answer there. So we get 6 plus 40 minus 10 plus d equals 0. We get d equals 46, 36, so -36 when we swing it over to the other side. And so we get our final answer of 6x plus 10y minus 2z minus 36 equals 0. And that is the scalar equation of that plane that they described. So for notes to yourself, explain the different parts of the vector equation of a plane. So you have the starting point and two vectors along the plane in different directions. They can't be collinear, is what I'm trying to say there. What information do you need to create the scalar equation? Well, you need a normal vector, an ABC, and then some other random point would help you solve for D. Steps to turn the vector equation of a plane to get the scalar equation. So take the two direction vectors and cross them. That'll give you the normal vector ABC, and then plug in the point, solve for D. And then adding those equations of a plane to your formula sheet. I think that's probably the end of the formula sheet. We'll see, should be. And then the practice you can work on in class.